As a molecule rotates around a single bond, sometimes it's forced to pass through unstable conformations. I'm Tyler Farah, and in this video, we'll learn how to rank eclipsed conformations by stability. We saw in the video about staggered conformation that staggered conformation is generally the most stable conformation, even though some staggered conformations are more stable than others. So in this video, we're going to learn about the least stable conformation, which is the so-called eclipsed conformation. And just like when a solar eclipse occurs and the moon stacks right in front of the sun, blocking the sun from our view, well, in an eclipsed conformation of a molecule, we're going to see that the atoms, the substituents attached to two adjacent carbons, line up so that they're stacked right on top of each other. The official formal definition of this is that the torsional angle between the two substituents is 0 degrees. And this is a little bit of a challenge to draw in Newman projection form because we still want to be able to see all the substituents for the accounting purposes, just being able to see what's attached to the molecule. So you'll often see the Newman projection drawn like this, not in a truly stacked up fashion, but in this way where we can still have a slight angle between two substituents so we can see what those two substituents are. The trick to this is you're meant to assume that this is a 0 degree angle, that these in the real world are stacked right up on top of each other, and that there's not even the slightest angle of separation between these. And that ends up being why the eclipsed conformation is the least stable, because these functional groups are going to have electron clouds. Electron clouds tend to repel each other, increasing the energy of a molecule. Energy breaks bonds. So if we stack functional groups up on top of each other, that's going to tend to cause a lot of what's called torsional strain. That word torsion refers to rotation, and since we're talking about a molecule rotating around a single bond, it's a very appropriate word to use in this circumstance. Now, I've drawn ethane on screen, and ethane is 2 carbons with a bunch of hydrogens. Hydrogens are small enough that ethane is not really going to feel a lot of strain. It's just going to kind of spin around like a top. But we're going to see an example of a molecule in just a moment that's going to feel a lot of strain when it is in these eclipsed conformations. And so before we do, notice that just like there are some staggered conformations that are better than others, well, there are some eclipsed conformations that are, I guess, least or less worse than others. We can't say any of these are better because they're not very good. The molecule is going to tend to avoid these conformations. But if we take the largest substituents and stack them right on top of each other, that's obviously going to cause the most amount of strain, the most amount of repulsion. And the term for this is fully eclipsed. This is the least stable conformation that a molecule can take as it rotates around a single bond, so it gets a special name. The other forms of eclipsed don't have a fancy name, but they are the next worst conformations. And so between the eclipsed conformations and the staggered conformations, we have the two extremes, the most stable for the staggered and the least stable for eclipsed. Let's take a look at an example. This is actually the same example that we saw in the video about staggered conformations. And I want you to keep in mind that if our molecule is going to get from a staggered conformation, where, for example, bromine is right down here, up to another staggered conformation where bromine is here, the molecule actually has to pass through this eclipsed conformation. So we've seen this molecule spinning in the past, and we kind of assumed it was just freely spinning, but the reality of that spin is that it's kind of herky-jerky. It looks a lot more like this, where the molecule sort of slows down as it approaches the eclipsed conformation and then speeds up into sort of click into the next staggered conformation. The result of this pattern, and we can watch it again, the result of this pattern is that the molecule spends more time in its, there it is, the stable state, and less time in the eclipsed, the unstable state. It kind of races out of the eclipsed state to get to the next staggered conformation. So, having seen that little bit of a visual, let's take a look at these Newman projections without the aid of our 3D model and see if we can rank these according to their stability. We know that the bromine and the chlorine are the largest functional groups in this molecule, and we see bromine and chlorine stacked up right on top of each other. That makes this a totally eclipsed conformation, totally eclipsed. and this is therefore the least stable out of all of them. Now, again, the other two eclipsed conformations are not super stable. They're the next worst conformations of this molecule. But even here, we can try to decide between these. And what it boils down to is considering the next largest functional groups on this molecule. If we take a look at the next molecule in line, we see that the largest functional group on the front carbon is lined up with the next largest functional group on the back carbon. And in fact, for that matter, we also see that the largest functional group on the back carbon is lined up with the next largest functional group on the front carbon. So here we're pairing the largest and second largest functional groups on each carbon and stacking them up together. That makes this, let's say this is the next worst. It's in the middle. And of course, by process of elimination, that leaves us with this one as the least worst conformation, or the most stable. But again, I kind of hesitate to use the word stable when we're talking about eclipsed conformations at all. So we'll go with least worst on this one. And the reason why is that in this case, bromine, the largest functional group on the front carbon, is paired with hydrogen on the back carbon. And similarly, chlorine, the largest functional group on the back carbon, is paired with hydrogen on the front carbon. So this is not a stable conformation, but it's the least worst of the bunch.